All right, let's dive into one of the coolest tools in all of statistics, the hypothesis test for a population proportion. Seriously, this is how we take a big claim that somebody makes about a huge group of people, look at just a small little sample, and make a really solid decision about whether they're telling the truth. So to make this real, let's treat this like we're data detectives solving a case. Here's our mystery. A company makes this big, bold claim, right? 35% of all consumers out there prefer our product. Now, how in the world do we check that? We can't ask everyone, so how do we use a small sample to see if they're right? That's the case we're cracking today.
You know, the logic behind this whole thing is actually pretty simple. It's a lot like innocent until proven guilty. We start by assuming the company's claim is true. We give them the benefit of the doubt. Then we look at our evidence, our sample. If what we found in our sample is just super weird, so unlikely to happen if the original claim were true, that's when we get suspicious. That's when we have enough evidence to say, you know what? I don't think that original claim holds up.
Now hold on. Before we jump in and start analyzing, you gotta know that every good investigation has rules. And a statistical test is no different. We have to check off a few boxes first, just to make sure our whole method is sound. These are what we call our assumptions or model requirements.
So here's our critical pre-flight checklist. First, and this is a big one, our sample has to be random, no cherry picking. Second, the sample needs to be big enough for the math to work properly. We check that with the little formula you see there. And third, weirdly enough, the sample can't be too big. It should be less than 5% of the whole population. This just makes sure our samples are independent. If we can put a check mark next to all three, we are good to go.
All right, with the rules out of the way, it is time to bring out the main tool of our investigation. This is the formula that's going to help us calculate a single score that tells us exactly how surprising our evidence is.
And here it is, the z-test statistic. Now, I know, it looks like a bit of alphabet soup, but don't let it scare you. The idea is actually super intuitive. The part on top, that's just the difference between what our sample showed, p-hat, and what the company claimed, p0. The bottom part just puts that difference into perspective. We're basically just asking how many standard units away from the claim is our sample result. That's it.
Think of this as the legend on our treasure map. Z0 is our final evidence score. P-hat is what our sample actually told us, P0 is the original claim we're testing, and N is simply how many people we talked to. See? Every single piece has a job to do in solving this puzzle.
Okay, enough theory. We've got our logic, we've got our rules, we've got our formula. It's time to get our hands dirty, plug in the numbers from our case, and see what the data is screaming at us.
So here are the facts. Our team went out and surveyed a random sample of 200 people. Out of those 200, 84 said they preferred the product. The company's claim, our P0, is 0.35. And finally, we set our significance level, alpha, to 0.05. Think of alpha as our line in the sand. If the probability of getting our result is less than 5%, we're going to call it statistically significant.
So, first calculation. We take our 84 people who said yes and divide by the 200 people we asked. That gives us our sample proportion, our p-hat, which is 0.42, or 42%. Okay, so right away you can see that in our sample, 42% of people liked the product. That's definitely higher than the 35% the company claimed. But is it different enough to call them out? Or could that just be random luck?
Next up, we calculate the standard error. This number, about 0.034, is super important. It tells us how much variation we should expect to see from sample to sample just due to random chance if the real number was actually 35%. It's basically our measuring stick for what's normal, random noise, versus what's a genuinely surprising result.
And now, the moment of truth. We plug everything into our big formula, and out pops our test statistic, our z-score, 2.0755. This is it. This is our final evidence score. This number tells us that what we saw in our sample, that 42%, is more than 2 full standard units away from the company's claim of 35%. That's starting to sound pretty far out there.
So we've got this score, 2.0755. But what do we do with it? How does that number turn into a final verdict? Well, there are actually 2 classic ways to do this. And here's the cool part. They're just 2 different roads that lead to the exact same destination.
Let's look at these 2 paths. The classical approach on the left sets up goalposts, or critical values. For us, those are at plus or minus 1.96. Our score of 2.0755 is outside those goalposts, so we reject the claim.
Now, the p-value approach on the right asks a slightly different question. It asks, what's the probability of getting a result this extreme? Well, that probability is 0.0379, which is less than our 0.05 line in the sand. So again, we reject. See? Two different methods, one single verdict.
This chart makes that p-value decision crystal clear. The p-value, which is the probability of our evidence, is that smaller bar. Alpha, our threshold for what we consider unlikely, is the taller bar. There's a famous little saying in every stats class, if the p is low, the null must go. Well, our p-value is definitely lower than our alpha, so that null hypothesis has got to go.
And there it is. The verdict is in. Case closed. Based on the strength of our statistical evidence, we officially reject the null hypothesis. In plain English, that means we have enough proof to say the company's original claim that 35% of consumers prefer their product is very likely incorrect. Now, this is how you'd write it up in a formal report. It sounds a little robotic, I know, but all it's saying is this. Look, our sample result was just too weird. It was too unlikely to have happened by random luck if the true number was actually 35%. Therefore, we have good, solid statistical evidence that the real proportion of people who prefer this product is something different than 35%.
Okay, before we wrap this case file, I want to give you a couple of pro tips. Think of these as rookie mistakes that are really easy to make when you're starting out, so you'll know exactly what to watch out for.
Okay, mistake number 1, and this one is super common, using your sample's p-hat when you calculate the standard error. You have to remember the entire test is built assuming the claim is true, so you must use the claimed value p0 in that formula. And mistake number 2, don't you dare skip checking those requirements we talked about at the beginning. If your sample isn't random or isn't large enough, your entire conclusion is built on a foundation of sand, and you just can't trust it.
So what's the big takeaway from all this? It's that this test is an incredibly powerful idea. It gives us a formal, step-by-step method to look at a tiny little piece of the world, a small sample, and use it to make a confident, evidence-based decision about the entire thing. It's how we go from just guessing to actually knowing.
And that's a wrap on our case, so I'll leave you with this final thought. Start listening to the world around you. You see claims on advertisements, you read them in the news, you hear them online. 4 out of 5 dentists agree. 80% of users see results. How many of those could you put to the test, just like we did today? The world is full of claims, and now you've got the toolkit to find out what the data is really saying.